Hello? Hello? Okay, so hopefully we can try to file in and find a seat and get started for the next session. I'm John Rabula, I'm going to be the chair. We have one talk and then some spotlight videos. Okay. Great. Okay. So I'd like to welcome Stephen McCrory from IHMC.
I'm Stephen, and I'm going to be talking about a two-stage footstep planner that we've designed here at IHMC and run on Atlas and Valkyrie. And this work was done with Georg and a number of other researchers here at IHMC. So here's an outline of the planner. So it takes in a user-specified goal and perception information from LiDAR and feeds this into a two-stage planner. The high level is a body path planner, so it does a kind of course approximation of where the body path should go, and this feeds into a low-level planner, which actually looks for footholds. And this planner is completely independent from the controller, so this is looking for a list of timed footsteps, and then this feeds into our controller, which navigates those. So here's some pictures that was taken running Atlas with this footstep controller. Main thing to note here on the top right, you can see so the LiDAR points are in blue, and so these are points that we feed into a module that does plane fitting and detects those colored polygons there, and that's what we plan over for the high and low level planners. And then on the bottom there, you can see the footsteps that are generated from the footstep planner. So what I'm going to do is start by talking about the low level planner, which is an A-star planner, and then talking about the body path planner. So some terms. So what we use is a lattice-based structure for our planning, similar to a number of other groups who've done footstep planning. We have a lattice, an X, Y, and yaw, and our discretization is usually about 5 centimeters for X, Y, and then 10 degrees for yaw. And we consider a node on this lattice to be a potential footstep in the world frame. And we have a nominal expansion, so given a certain footstep node, we just have a static list of what we call children footstep nodes. So the stance foot would be on the left, and then there's just, given the rough kinematics of the robot, we have an array of children footsteps. And to go from this lattice representation to position and orientation, we have a snapper, and so that takes in this point on the lattice and just snaps it to the planar region. And then we have a checker, which just, after we've snapped the footsteps, checks given maximum step height and step length, what the if the step is valid, because the the lattice is in just a planar representation. And then we also have a cost calculation based on these snap steps. And usually what we use is just a simple heuristic for distance and a yaw weight. One note, kind of an edge case for the lattice representation. So suppose you have a cinder block here that doesn't really line up with your lattice, so you have to have the footstep land on the cinder block. You don't have a lot of extra room, but that lands right in the middle of your lattice. So this is kind of the biggest fallback of using a lattice representation. So the way we get around this is we have what we call a footstep wiggler. So given a footstep node and then a potential foothold, we set up a QP to wiggle this footstep into the foothold given within the node's cell. So given the discretization, it can move within before it's in a neighboring cell. So quick note on the timing. So this wiggling takes quite a while compared to snapping. So in practice, what we do is we just have a threshold of about 60% while we're planning. And then after we get a good plan, then we try to move these footsteps into better footholds. So a video here of Atlas going over cinder blocks using this planner. This plan took under a second to plan. I don't have the exact time, but they're usually in the range of about half to 1 second. Okay, so that is our low-level planner, and then I'm going to quickly go over how this integrates with the body path planner. So our body path planner uses the concept of visibility graphs, which is if you have a 2D world like this and you have a number of obstacles, a visibility graph is just a graph constructed of intervisible nodes where the nodes are vertices on your obstacles or positions you want to be at. So for this little world here, it'd just be these edges, and then you can run any graph search you want over those. So in practice, here's some planar regions we got from a set of cinder blocks, and you can see we just put nodes all around these planar regions, and we identify obstacles based on the threshold of the planar regions, say those are no-go locations, and we also prevent nodes from being put around those obstacles. So it takes, it actually doesn't take too long to run this. It takes about 1.2 seconds on average to construct the world and do a A-star plan over this. So you can see on the right is the body path plan generated. So the way this integrates with our low-level planner is what we do is we take in a set of planar regions, plan a body path, and then look forward at some horizon, usually about 1.5 meters, and then feed that in as the goal location to the footstep planner. And this also is integrated in the heuristics of the footstep planner. And it usually doesn't make too much of a difference, but if you're, in this case, if you're turning to the left with your body path plan, that'll tend to make the footstep planner yaw those steps to the left. So our goal in this framework is to set up a dynamic planning structure. So if on the left here you have your gate, what we try to do is at the start of every swing, queue up the planner, which is running asynchronously from the controller, and run that planner. And then after it generates a plan, we send it back to the controller, and it updates the plan. And you can see Valkyrie there in the animation doing that. Every step, it overrides the current plan. And one more video of Valkyrie replanning as obstacles are placed in front of it. And there we go. Questions?
You have questions?
Just practically speaking, how big of a space in front of the robot do you think you need to scan and analyze and plan over in order to make it a usable general mechanism for you?
So I think so the 1.5 meter horizon we use for the actual footstep planner has worked well so far. So I think I guess the big question is if you want to try to navigate, if you're in like a hallway versus some area with rougher terrain. If you're actually planning a complicated body path, you need more area, but for the actual footstep planner, 1.5 meters is fine in practice, I think.
Can I ask the people who are have spotlight videos to come up so you can be held responsible for it while it plays? Are there any other?
Sorry if I missed that part, but when you do a wrong step due to a disturbance during the footstep planning, how does it update the plan? Do you replan?
So yeah, actually, so what you do is at the start of swing, you tell the planner to plan from the desired touchdown, and then even if you miss that, usually it's not going to be more than a few centimeters. Then you can still reach the next footstep after that. But your start node is the anticipated touchdown. So.
Okay, let's thank our speaker again.